So here we have a problem. Find and classify the critical points of the multivariable function f of xy equals 3x squared minus 2xy plus 1. And this is a common problem that you will see in multivariable calculus. So let's get right on with it. The first step we should take in solving this is the first question asks to us to find the critical points. Find the critical points, and later we can go on and classify them. And if we remember from previous videos, the critical points of a multivariable function occur when the gradient of that function, equals 0, boldface 0, meaning the 0 matrix. This means that there is a flat plane, so either we have a maximum, a minimum, or, if we remember, a saddle point. But we'll go on to classify our critical points later. For now, let's just find them. And we can find them by expanding out our gradient. If we remember, the gradient of a multivariable function is just the matrix with the partial derivative with respect to x of that function and the partial derivative with respect to y of that function. And because we know that this equals the 0, 0 matrix, we are going to have a two equation system that we will be able to solve. So let's get on with this and plug our function in. So let's get a nice color here. The first equation is that the partial derivative of f with respect to x will equal 0. Well, let's go calculate the partial derivative of f with respect to x. This equals, well, 3x squared becomes 6x. Minus 2xy becomes minus y, right? The y looks like a constant and the x goes to 0. And then the y looks like a constant and it goes away. And we know that this equals 0. Now, the partial derivative of f with respect to y equals, well, the 3x squared entirely looks like a constant, so it goes nowhere, it goes to 0. The negative 2xy term, now the x looks like the constant, so the y goes to 0, and you get negative 2x. And plus 1y just goes down to plus 1 equals 0 again. And now we have a two variable system that we can work with. So let's start with the easier equation here. Negative 2x plus 1 equals 0. Well, if we add 2x to both sides, we find that 2x equals 1, and this is great. X equals 1/2. That is what this equation tells us. So we've found that if this right here is a graph of the xy plane, x will equal 1/2 at all our values. And we can use this fact when we also know that the partial derivative of f with respect to x has to be at some value, and hopefully we can find some sorts of intersections with this that will give us our critical points. So let's go on and calculate the 6x minus 2y equals 0. Well, we know that x must equal 1/2, so we get 6 times 1/2 minus 2y equals 0. Well, 6 times 1/2 is 3, and if we add 2y to both sides, we find that 3 equals 2y. Well, this right here just implies that y equals 3 divided by 2. So, for this multivariable function, 3x squared minus 2y plus y, we have just one set of critical points, just one critical point at the point 1/2, 3/2. Well, this is great, but now we have to ask ourselves the question: is this point a maximum? Is it a minimum? Or is it a saddle point? And to do this, we will use the second partial derivative test. And if we remember the second partial derivative test, what the second partial derivative test told us is that the partial derivative of f with respect to x, and I will actually write it in this notation, the second partial derivative with respect to x. So partial derivative of f with respect to x, and then the partial derivative of f of that partial derivative, again with respect to x, times the partial derivative of y with respect to y. And if we subtract here the partial derivative with respect to x then y times the partial derivative with respect to y then x, which will end up being the same value. If this is greater than 0, then we know we have a max or min. We know we have a max or min. But if the second partial derivative of f with respect to x times the second partial derivative of f with respect to y, if this minus this here, this here is less than 0, we have a saddle point. Oops, not two O's. We have a saddle point, and if it equals 0, then we don't know. The second partial derivative test is not enough to tell us what the point is. So let's go on and calculate this here. So the partial derivative of, let's scroll to get some room here. If we knew that the partial derivative of f with respect to x was 6x minus 2y, then the second partial derivative with respect to x is the partial derivative of this expression right here. And, well, as you can see, the y looks like a constant. The 6x just goes to 6. And here, the second partial derivative, if we say here, second partial derivative of f with respect to y, this here equals, well, negative 2x looks like a constant, 1 looks like a constant, so this equals 0. So fxx, let me draw this slightly larger, fxx times fyy, this equals 6 times 0 is 0. Let's calculate the mixed partial derivative terms now. So we'll find that the mixed partial derivative, where we first do derivative with respect to x, then y is asking us if we take the derivative with respect to y of this expression here. And, well, what do we get? We get negative 2y, negative 2. Negative 2y goes to negative 2, and the 6x looks like a constant. So this here equals negative 2. And the partial derivative of f with respect to first y, then x, this is asking us to take the partial derivative with respect to x of this expression, which is, well, negative 2x goes to negative 2. So we get, again, negative 2. And if we multiply these together, we get negative 2 times negative 2. Well, this equals positive 4, but we are subtracting it from f, second partial derivative of f with respect to x times second partial derivative of f with respect to y. We subtract off our mixed partial derivative terms. We subtract off our mixed partial derivative terms, and we know that this first term equals 0, this second term equals 4, and this will equal negative 4. And negative 4 is less than 0. So we can conclude, in conclusion, that we have f of x, y has the critical point at 1/2, 3/2, which is a saddle point. F of xy has a critical point at x equals 1/2, y equals 3/2, and it is a saddle point because the second partial derivative test was less than 0, and it is a saddle point. And this is one example of using the second partial derivative test to find and then classify the points of f of xy equals 3x squared minus 2xy plus y. So I will see you in the next video.